Okay, so we are recording. So we're going to take a look at 3.6, number 3 on the classwork, just as an example to kind of tease it out. And this problem said, part A, you get into the system and you practice a little bit with that. But if you have the same mass on the same spring constant with no damping, you'll notice that the pattern between these two, wobbling around, pretty much stays constant, always. And so it's pretty boring because they are literally the exact same harmonic oscillator, so they're going to have the exact same period. And since there's no decay, because there's no damping, it's kind of boring. So if I hit stop up here and get them to basically just sit at their rest position, and so their natural length is there, but their equilibrium position is here. So this is where they are, and that's their rest position. What we can actually do is get a sense of what's going on by taking a look at and measuring the distance between their natural length. Like if I remove the spring, we take that spring off, the natural position is here, and the equilibrium position when I add 100 grams worth of mass is right there. And so it's probably too small for you to see on my screen, but I'm looking at it and it looks like, oh, I don't know, ballpark, given the precision on the scale, I'd call it like 11 and a half millimeters. That would be what I'd use for my distance. That's how much distance the spring is stretched by 100 grams worth of mass. So remember those two numbers, 11 and a half millimeters.
Would that not be 16 and a half right there?
It would be, yes, because I can't read. And thank you very much for pointing that out. It would be 16 and a half ballpark millimeters of stretch for 100 grams worth of mass. Remember, mass isn't what does it. It's the weight. It's the force that does the stretching on the spring. So if I switch over from sharing on that to sharing on my document camera, we can say that 16 grams of mass is equivalent to how much weight? How could we figure out how much that weighs? What's the relationship that we can use to figure out weight?
Multiply it by gravity.
Yeah, weight equals mass times gravity, right? So weight is going to be its mass, which in grams, we'd probably want to convert that to kilograms. That would be 0.016 kilograms. And the gravitational constant in the SI system is 9.8. You can call it 9.81 if you want, meters per second squared, depending on where you're at on planet Earth. It doesn't vary that much, but a little bit. So if we've got both of these numbers, we can figure out, let me get rid of this, all this junk you don't need on the screen there. We can figure out what the weight is, approximately, I don't know, 10 times this would be like a little bit smaller than 0.16. So I'm going to call it 0.15 just for the sake of argument, because I'm basically multiplying by 10. So ballpark. And let's call that newtons. That's the weight. And that stretches the spring. What was it? 16.5 millimeters, right? We measured that, so it's 16.5 millimeters. So the stretching of the spring thing combined with the weight, we can actually figure out what the spring constant is. Because if you remember, Hooke's law says that the restorative force of the spring is equal to the spring constant times the distance, x or y, whatever variable you're going to use for that displacement. Right? And technically it's negative, but we don't care. For the purposes of what we're doing, we just want to get the absolute value of k, how big that is. And so that means to figure out what the spring constant is, we just need to take our force, how much force, and divide that by the distance or the weight, and divide that by the stretchy distance. How much did it stretch? So in our world, that's going to be equal to, 0.15 newtons divided by this. But in order for the units to really kind of play nice together, we're going to use a distance unit of meters, which this is going to be a real small number. So this is going to be, what is it? What would it be? 1, 2, 1 gets us to centimeters, and then 2 more gets us to meters. So 0.0165 meters. And so that right there, this represents the spring constant. And notice the units are newtons per meter. It's basically telling me how hard does this spring fight a stretch. Well, for every 0.0165 meters, it puts up a fight of 0.15 newtons. Right? That's how hard the spring is kind of fighting back. And so I don't know what this turns out to be, but let's say they're roughly equivalent to each other. So ballpark, this thing is like 15 divided by 1, because they're roughly the same thing. So it's, if I move the decimal places over, on top, move it over 2, and the bottom, move it over 2, ballpark, this thing is going to be like 1 Newton per meter. Really ballpark, because I don't have a calculator. I'm sitting in front of a really fancy computer, but I don't have a calculator. So I'm really lazy. And I know you guys don't have any calculators or any fancy computers, and none of you are volunteering to do my calculations for me.
9.09.
My dog is pissed off. She really wants you to do calculation. So what does this thing turn out to be? Let's say I didn't cheat up here and say that that was equal to 0.15. If I do that multiplication, and then I divide 0.15 Newton, or that divided by 0.0165, what does it turn out to actually be closer to? My goddaughter's here from medical school. So
0.9, wait a minute. I grouped up, hang on.
I mean, 0.9 something makes sense because ballpark close to 1.
0.9556.
Not bad. Not bad for a couple of kind of goofy approximations. By the way, those of you going into any kind of physics class, this is pretty much what your physics professors are going to do when they run into calculations. They do not pick up calculators. They go, that's just basically 1. And they just wave their hands and make it go away. It just makes it easier. Engineers do that, but only after they've run the calculation and they go, oh, so it's basically 1. So this is my K value. And that means I now have a way of being able to write my undamped harmonic oscillator equation. Because you remember the undamped harmonic oscillator says mass times the second derivative of position. There's no middle term, there's no damping, plus K times Y is equal to 0. This is the undamped harmonic oscillator, really, really boring, right? And we know the mass that's sitting on it, or I think it's given in the problem. It says basically, later on. Oh, no. Oh, yeah, okay. Oh, I'm confusing that problem with another one later on that we're going to do where we actually make the measurements and stuff and then we put it in there. But let's say we're going to use our 100-gram mass, or 0.1 kilogram, plus our K, which is, I don't know, 0.956, call it, Y, equals 0. This thing right here, we could then hop over to Maple, say, hey, Maple, will you desolve this with a couple of initial conditions? If I give you initial conditions, it can come up with an equation that solves this, and it will predict our position function. So for example, let's say we're going to release it with 0 initial velocity from a position, a stretched position of, I don't know, let's say 5 centimeters, right? So just in case you're wondering, we can see what that looks like by coming over here and saying, hey, Maple, not hey, Maple, hey, computer screen that you're doing stuff for us on, the lovely little see if I can switch over. Where the heck is my screen? Sorry. New share. There we go. That's where it is. So if we go over here and I can say I can pull this 100-gram mass down 5 centimeters. So it'd be like right about there. Is that 5 centimeters roughly? Thereabouts? Hold on, let me do this. Let me hit stop. Then I'm going to do a movable line. And I'm going to slide this thing up to 5 centimeters, which should be right about there. And so I'm going to stretch this thing here, and I'm going to release it with 0 initial velocity. And you can see we've got a very predictable motion going on. But we can ask Maple to make a prediction for that. So if we wanted to, we can step over to Maple. So I'm going to play this out to the very end here. I'm going to step over here and say, hey, Maple, can you desolve this juicy bit of differential equation? And I'm going to cheat and use the calculus over here. Second derivative of y of t times 0.1 plus 0.956 times y of t equals 0. And we've got, oh, I should add my little bracket in the front because we're going to take initial conditions. And our first initial condition is our initial position is going to be 5 centimeters, which by the way would be 0.05 meters. And our initial position, or excuse me, our initial velocity, y prime of 0 is equal to 0. And so Maple's going to think about this for a second because it's my computer, and Maple on my computer always just takes a little bit longer to think about things. And it says, here is your position equation. And so we can tell just by looking at this thing that it has an amplitude of what?
1/20th?
1/20th. Now, 1/20th as a distance unit would be the same as what decimal value in meters? 1/20th of a meter is
0.05.
whew, okay. Yeah, 0.05. Remember that spring that we pulled it, we stretched it 5 centimeters below its rest, or its equilibrium.
Oh my god.
What's that? Did you just realize that 1/20th is the same as 0.05? Yeah, okay. Yay, good. So 1/20th of a meter is the amplitude. So if I was in here and I was, writing this for later, I'd say the amplitude of motion equals 5 centimeters. And what about the period of motion for this? Because this thing definitely has a period. What's the period? How would I calculate that? I'll give you a hint. It's inside the cosine.
Would that be 2 pi over the square root of 239 over 5?
Yeah, 2 times pi over the square root of 239 itself divided by 5. And you're like, oh, that's kind of ugly. But that's what it is. That's the period of motion. Now, if I want this thing approximated, I could say, can you give that to me? Oh, where's my stupid little, there it is off to the side here. Can you approximate, Maple? Good God, Maple. Approximate it out to 5 decimal places, and Maple says it's, oh, it doesn't like my use of lowercase pi. Whoops. Uppercase pi. There we go. As 5 decimal places, badonk, 2.0322. So Maple predicts that it's going to take about 2 seconds, a little over 2 seconds, in order for this thing to complete a full circuit. So if we switch back over, let's see how well we did in terms of our modeling reality on the screen here. So let me switch back over to this. It should still be going. Notice we pulled it down to this point right here and released it, and you can see that it seems to be going about, well, from up there There's one. To down, where's this one going? Right about there. Right about there. Ballpark. So a total distance of, about 10. So its amplitude is about half of that. It's about 5 centimeters. And if we wanted to, we could pull out the stopwatch and say, hey, okay, I'm going to try to, wow, we're way off. Our model doesn't do a very good job of predicting. And the reason for that is because this isn't a harmonic oscillator where it's just the mass and there's no outside force. It's just the force of the spring. There's actually a second force going on with this guy right here, and that's the gravitational force. So in the event that we wanted to see how this works out in reality, I can reduce gravity to none and then stretch this thing 5 centimeters or thereabouts, release it, and see what happens. Notice a 5 centimeter stretch with no gravity, just wobbling back and forth, no damping. It's a little bit better. Now, my ballpark estimate of stretch distance and my ability to measure with this particular scale, it's forgivable. Right? But we can model reality based on our equations that we come up with here. So it's pretty handy. Yeah, okay, we're off. Just based on the counting of the periods. It's not very close in terms of the periods, but yeah. Our estimate ballpark. I blame measurement error. It's always safer to do that. So back to the point of all this, being able to model reality, be able to solve and get the value for the spring constant, which is, let's see, switch back over there. Starting with knowing how much mass and what its weight is, we can calculate the force and measure the distance that the spring stretches, and from that come up with a spring constant. And as soon as you have a spring constant and you know there's no damping, then you have your undamped harmonic oscillator equation, which you can then use to make predictions till the cows come home. Or if the cows are harmonic oscillators until they come home and then leave again, and then come home and then leave again, and come home and then leave again. And if there's damping, eventually they'll just stay home. Or they'll stay gone. I don't know. It depends on where the rest position is. Any other questions on that? Either 3-6 classwork or questions on the Chapter 3 review? That's kind of what we're looking at right now before we go diving into the problem set 10. No. Okay. Well, what I'm going to do now is give me a second to make some breakout rooms. We're missing a couple of people here. I assume it's because it's just before the start of things, so I'm going to give them a couple more minutes to show up before I make the breakout rooms, because adding people after the fact is kind of a pain in the tuchus for the breakout rooms. Now that people are coming, we have a couple more people. What'd you get from McDonald's? Was it good? Chicken nuggets? Are you a chicken nuggets girl?
Sometimes, but Wendy's nuggets are better than McDonald's, so.
Are they really? Who
I
has the
think
best
so.
nuggets?
I like Burger King's.
Really? The
Yeah.
tenders? The
Is that
tenders are
even
good.
chicken?
How about Chick-fil-A? You guys had Chick-fil-A?
Chick-fil-A's the
Yeah.
best.
I never go there.
No question. Popeye's the second.
Popeyes. Did you know that we're getting a Popeyes in Jackson on West Ave?
I'm gonna be broke after that.
I don't think I've had Popeyes, God, since maybe undergraduate. It's been a long time. Yeah, it's been a long time. Wow. So who makes the best, just straight up, best plain, nothing, no frills, basic hamburger? If you had to eat a hamburger, if you're into eating meat, who would you get a hamburger from if you had to choose? It's got to be fast food. No sit down. Just
Five
fast food.
Guys.
Five Guys? Interesting.
Does
Okay.
Five Guys count as fast food though?
Are
Yeah.
there drive-throughs for Five Guys?
Okay, then
No.
I'd choose Five Guys if there's drive-throughs.
Okay.
In the fast food.
Nobody votes for Culver's?
That was going to be my vote, but I wasn't considering Five Guys.
I feel like I might be a little bit too biased in this one. So
Do you actually like the food at Culver's?
I personally, I consider Culver's the best fast food restaurant in Jackson.
Interesting.
And
you still eat it. You still eat the food.
I still eat the burgers. I've been there for a year and a half, and I still eat the burgers every.
See that right there, that's a sign. Usually whenever I talk to somebody and they're like, I've been working there for a year, I'm like, do you eat the food? If they go, nah, then I'm like, okay, I think I'll skip it. I think I'll skip it. I do that with pizza all the time.
I still really like the burgers. But if Chick-fil-A came to town, then I would jump ship immediately. Like, let's be honest here.
Yeah, I was really surprised that they haven't put one in yet. I would think like right at the 127, 94 interchange, somewhere in that area, a Chick-fil-A would just kick butt. They would make so much money. That place would be crazy busy.
Culver's would lose a lot of customers. Like half of our customers are a bunch of churchgoers on Sunday.
Oh, really? Is it super
We get a
popular on
lot. We
Sunday?
have a huge after church rush. It's
Culver's is the place to be. WWJE. I guess we know. Anybody else work in a restaurant, food type place? Nobody? Really? Interesting. I worked at a pizza place when I was in high school, and I thought I was going to I loved pizza when I was a kid. Of course, you're a kid, you love pizza. And I thought, okay, I'm going to work there and I'm going to hate pizza. Oh my God, I loved pizza so much. And every day that I would work, I would eat more pizza. It was so delicious. And it really wasn't that great a pizza, but it was just, God, reinforced my love for pizza. But interestingly enough, every day I would work, I would get like a stomach ache. And so like 3-4 hours after I started working, I'd have this terrible stomach ache, like horrible stomach ache every time. And, I'm young. I don't think anything of it. Later on in life, I discovered, you idiot, you have gluten intolerance. Yay, I have celiac disease. And so I was basically poisoning myself at work. I'd be like, yeah, sure, I'll have a slice of pizza. Like, sure, give me some of that arsenic. Oh, this is so good. I love this arsenic. Oh, God. So listen to your body, I guess is what I'm saying. That's the lesson for today. Listen to your body, even if it's not a harmonic oscillator. And that's the transition, a chance to talk about harmonic oscillators. So last call, any questions on the chapter 3 classwork or chapter 3 exam review? Did you get a chance to look those over, or were you busy doing other things this weekend? How dare you? How dare you? How dare you? That's right. You skipped it. Okay. Well, we're going to take a look at the problem set. And my plan, just for those of you who are joining us now, my plan is I'm going to reopen the problem set through 11:59 tonight. So you guys are going to have a chance to work specifically on a problem. Then we're going to get together and go through the problems, make sure that we understand them. And if you see or hear something and you're like, oh, man, I must have really messed up that problem, I want to fix mine, or you want to add something to it, that's totally fine. You can go back and resubmit. I think it'll allow you to submit another one. Or if you just want to email it to me, that's fine too, either way. But sometime tonight. But at 7:15, you're going to get a scheduled little remind message with the exam. So you will have the exam to work on at 7:15. If you want to take a little bit of time and finish up the problem set, that's fine. You can do that too. But the exam you'll have at 7:15. And I have to be out of here in an hour. So let's get cracking. Is everybody clear on which problems you're going to be responsible for? Everybody knows, everybody sees which one you're going to be working on? Yes? Chris, Austin, and this group is John and Quentin. Sorry, I'm just trying to do this. I can't talk and work at the same time. Bryce and Matt. Okay, so I'm going to open up the rooms. I want you guys to get in there, work with your team. I can float around and answer any questions, but the name of the game is you're going to have this ready to present in half an hour.
Whoa.
Hey,
If you hold your right to the roll, zoom in and out.
Yeah, for a PC, it's hold down Control and then mouse wheel. For a Mac, it's Command and mouse wheel, and that works too.
Yeah, that's what I was using, but the right click and scroll is way easier.
Oh, I didn't know that. I'm gonna have to try that.
It's pretty nice.
I wonder if it does that. I can't do that on a PC. Must be. Oh wow, yeah, that really is easier.
It's pretty nice. We got, while you're here,
Yeah, sure.
we do have a quick question.
Sure.
Right here, in we're finding the general solution for
Find the GIS.
part
Yeah.
A.
Find the GIS.
This, we got two different solutions.
It is possible to get two that appear to be different in the general solution only because that constant can absorb all manner of sins, right? So you can have something times the constant, or you could have a constant that is sitting, oh yeah, constants are sitting in a different place. So let me see, what did you get here? Desolve. Well, you can't desolve something that's not an equation.
So we need to set this equal to 0?
Yeah, you know what though? I think Maple presumes that you're setting it equal to 0 if you do that. So it should be okay.
We got the exact same thing.
Yep. So when you say you got, okay, so the first one is not the same as the second one. So, oh, you know what? I don't know. Is that the shortcut code for second derivative? Is it
the
comma
double
t, comma t?
I believe it is.
Is it?
Diff f x. It says $2 for some reason.
Yeah, I think that's what it would have to be. Dollar bills, y'all.
$2. Did they want like a comma in there or something?
I don't know. That's really weird.
That is very odd. I'll put like a space, I guess. That looks exactly the same.
That's weird. Yeah, the way I always do it is I always do nested. So diff, and then on the inside, another diff, y of t comma t, and then outside comma t. So that's why I don't like typing it. It takes forever to type, but there's probably like 3 different ways to do it. So that's odd. I'm going to assume it's Maple rounding things and go with the first solution. So yeah, so you might have a simplification. So 95, does 95 factor out anything?
We tried putting it on decimals, but not next to each other.
That's really weird
Like-
because it should have an exponential involved too. So where the heck did the exponential go?
I got the bottom one too. The
Interesting.
desolve, the sine
Yeah.
to the square root of 6.
Wyatt and I were trying to tackle this earlier. For
Well,
class.
there's damping, so it should involve some exponential decay. Right?
The 95/8 one I graphed, and it seemed to work. I just assumed both constants were 1. Like
Yeah,
the general-
that's fine. Yeah. Yeah, general solution should work for any values for C1 and C2. It shouldn't work, that second one should not work because it's not exponential, there's no exponential decay involved. It's just oscillation. And so it's almost like that's saying it's almost like it's saying that's not damped, and I don't know why that is. So when you typed in the d over dt, did you use the palette on that one, or is that?
For this one, yeah, I used the
Yeah.
palette.
That's
When I
weird.
did mine, I defined it as an equation. So I said EQ12 equals, and then typed out the D,
Okay.
and then desolve the EQ.
Okay, yeah. So I guess the test would be try putting initial conditions in and see if you get the exact same solution. I mean, it looks like you shouldn't based on the general solutions that popped out. But
Yeah,
I
it
mean, the
looks-
exponential decay definitely needs to be there because it's a damped harmonic oscillator. Even if it's underdamped, you'd expect it to be. Yeah, yeah. The blue one is just undamped, and so it looks like they have the exact. No big surprise, they have the exact same period of oscillation, but the blue one is undamped. So that's really weird. I don't know why.
Probably the better idea to go with the first one.
Well, I mean, simply because it's we know that it's damped, then yes is the answer. But let's take a look at maybe there's something in the code that we're missing. Something maybe we're not spotting. Here, you know what? Just leave that there. I'm going to try typing the exact same thing in my Maple and see if I get the exact same result. So. In the meantime, you guys pretty confident about your solution on number 6? Feeling good about it?
I'm pretty confident. I'd feel more confident once we compared answers, but personally, I feel confident.
Well, did you get the same result for the end result for the predictions and stuff like that?
We haven't checked yet. We got to
Oh.
A, and we said, "Oh, we have a problem here," and we haven't gotten past it yet.
So, and I'm holding you up here. Hold on. I'm just curious. This is professional curiosity here. Cavity plus 3 times 5t equals 0. Okay. Mine's giving me the exact same result for the first equation. And
Oh, I added a space.
Let me try then.
no, that's not it.
And there was a space missing here.
Where?
Oh, is
Between the
that
1/2
seriously?
and that was it.
What the heck? What was it doing?
Didn't even add a, I don't know.
That's really weird. I genuinely have no idea why. It was treating it like there was no damping term. So that makes sense because that solution is with no damping.
Yeah.
And that solution is with a damping term. Hey, mystery solved, but still really strange.
I'm gonna look for one and see if I can figure mine out too then.
Okay, well, keep plugging away. I mean, at the very least, when you're presenting your solution, I'd say leave that in there just for the sake of, hey, look at this really weird artifact. And the way I knew this was the right solution and the other one was not is because it's got a damping term, so it's got to be exponentially decaying as a harmonic oscillator. So Yeah, leave it in there with that weirdness, and then we'll go from there. Cool.
Sounds good. Thanks.
No problem. I'm going to scoot over to another room.
Type this whole thing. I'm not going to copy and paste.
Okay, so we're back from our breakout rooms, and we're going to start taking a look at problem set 10. This will be the key by which I grade all assignments. So problem number 1, take it away. I'm kidding, right?
That's going to share his. Yep, perfect. Okay. Matt, can you show the problem set or no?
It's okay. I mean, everybody's got access to the problem. They
Okay.
can click over. This was a following linear system, and so up at the top, it looks like you have the coefficient matrix for it. So go ahead, take it away.
So the coefficient matrix was 0, 1, -1, -2. So
Okay.
we first started off by taking the determinant with the lambda. So then we get 0 minus lambda times -2 minus lambda plus 1. So then we factor that out. We got the lambda squared plus lambda, 2 lambda plus 1 equals 0. So then after factoring that out, you get lambda plus 1 times lambda plus 1. So it's basically lambda plus 1 squared equals 0. So then our lambda is -1 repeated. So then we know, so after that, we know we can use a valid. And then our V naught, and then our V naught equals, or X naught, Y naught in the matrix. And then we basically just plugged in our lambda in for our lambda up here in the coefficient matrix. And then we just solved it out, multiplying it by X naught and Y naught, and got this guy.
So the only thing I would add right there is technically you've got V1 equals this thing and then another equal sign. Technically that does not equal what comes after. So V1 equals that matrix with the lambda in there. Yes, that's correct. No,
Yep.
not that one, the one before. Yeah. So that is correct. That was equals.
This one right here.
The previous equals. Yeah, the previous one isn't an equal sign. Yep. That's one. That's not an equal sign. There you go. And so what you're doing when you find that modified coefficient matrix times the initial conditions, you're coming up with that special matrix for our ballad solution. So good job. So part A is the general solution.
Yep. And then we just plugged in this, what we get from the ballad, into the general solution right here. And we know, I think our T up here, Matt, should be -1 or a negative T.
You caught it. You didn't even give me a chance.
Yep, that should be negative T.
Yeah, because your lambda value is -1. So in both cases.
Both of them too.
Yep.
Yep.
Good catch. The way I was going to have you notice it was I was going to say, what's the one thing that you didn't do in your question solution that probably, given the computer program that you're on, would be a smart move to do at the very end anyways?
Mm-hmm. I don't know.
Really? You have this wonderful, wonderful computer program?
so?
Yeah. You should be able to desolve that system of equations and verify that you get the equivalent in parametric form of the matrix solution. You don't have to do it right now. I'm just saying, if you have the ability to come up with the solution through Maple and you don't do it to check your answer, it's like leaving money on the table, right? Don't do that, especially on the exam, right? Notice I'll say, I want you to do this by hand, but that doesn't mean I don't want you to check it. So I'm operating under the assumption that any solution that you turn in for these by hand solutions, you've checked with Maple. And if you haven't, it's like not using your safety net. So for part B, it's really as easy as doing what?
We're just plugging in our initial condition.
Yep. Just plug in your X sub 0 and your Y sub 0 and go to town.
And
So
that's all.
the only other thing that I would say would be make sure if you have the ability to check your solution, and you could do that at the end of part B, just do a desolve with your system with your 2 initial conditions, and you should get the parametric equivalent of your matrix solution. Absolutely. So nice. Any questions on that one? Hopefully you've had a little bit of practice using the ballad. And now you know why I call it just the ballad, because if you had to say, oh, it's the formula for solving the repeated eigenvalue, it's unique, it's special, so it needs its own special name. Just so you know, no one else calls it the ballad. So when you go on to your future math classes and you say to your professor, oh, are we going to use the ballad of the repeated eigenvalue? They're going to look at you like you have lobsters crawling out of your ears. No one else calls it that. Or alternatively, if you start using it more often, maybe we can spread the good news of the ballad, and soon everyone will use it. What do you think? I was not buffering just there. I was just looking like a dope. Okay, number 2, since there's no questions on number 1. Number 2, take it away.
Okay, I'm going to screen share and Emma's going to explain.
Oh, I wonder if her computer's gonna break. Uh-huh.
No. I showed you. I have
Did you
2
fix it? Did you
set up.
figure out what was going on?
Nope.
Still no idea.
Nope. And I don't even take the risk now. I just start right up with the other one.
You got it. Fire away.
Okay, so for part A, you just wanted us to find the eigenvalues and eigenvectors with Maple, so that's pretty straightforward. As you can see there. Hold on, let me mute this TV real quick. I'm sorry. Can you hear it?
It's a little tinny in the background.
Oh, okay. Well, is it a problem?
Well, if anybody else is there enjoying it, then yeah, it's a problem.
Okay, so those are pretty straightforward. The eigenvalues are D and A, or A and D, and then 1, 0, and 0, 1 for the vectors. And then for part B, we had to sketch a phase portrait with an example values of A and D being equal and less than 0. So here we use -2 for that value, with some random initial conditions, so you can see the way the phase portrait's going. And then we found the general solution. Just a simple desolve with Maple, and then put into the one big general solution with y of t.
Nice. The one thing I will say is notice they actually found the general solution, and they did it 2 ways. They wrote it out in parametric form thanks to Maple, but then they also wrote it in matrix form based on their straight line solutions, right? Their eigenvalues and eigenvectors. Can you scroll up real quick to the phase plane? So how can we tell, looking at that phase plane, what our eigenvalues are? That our eigenvalues really are -2 and -2. How can we tell that our eigenvalues are negative?
Because they are going towards the center, towards the origin.
Everything's headed towards the origin. So it's a sink, right? Both of the eigenvalues are negative, real values. So it's a sink.
Yep.
Nice. Cool.
C was another phase portrait with A equaling D, and they're both greater than 0. So we use just +2 this time, which we can see because all the initial conditions are going away from the origin or a source.
Yep.
And then we found the general solution again with just the desolve and then the big y of t.
Nice.
And then part D was just comparing contrasting the 2 graphs or the phase portraits, and really they're pretty much the same, but you can just see the direction, whether they're going away or towards the origin to be a sink or a source accordingly.
Nicely done. Any questions on that one? All right. while I was driving at was this idea that if you have the exact same eigenvalues, but they're opposite in sign, it's a very predictable outcome for the phase plane. And it would be predictable even if they weren't equal to each other, as long as they're both negative in one case and both positive in the other, you'd get the exact same but in opposite direction solution curves on the phase plane. So nice work. Number 3.
I'm going to talk about it. Quentin is going to share the screen. There it is. Okay, hang on, let me move this. Okay, so we did number 3, and this was the problem. And so, right, yeah. And so we presume that d of y over d of t equals vt, or equals v or vt. And then, so there's that, and then we move, once that's there, we make that equal to everything else, which is negative 20y minus 4v. And then we put it in matrix form, and then we did, we separated it equal to 0, and then you get lambda squared plus 4 lambda plus 20 equals 0, and then you use the quadratic formula, which is always fun, right there, and then you do the math, negative 64 and then 4, so it's negative 2 plus or minus 4i. So then our y of t is...
So can I stop you right there real quick?
Sure.
Based on what the eigenvalues are, what kind of damping do we have for our harmonic oscillator in this case? So you've got a complex eigenvalue with an imaginary part. What does that tell you about the damping situation? What do you think, Quentin?
Isn't it underdamped?
Yeah. The only way you're going to get imaginary eigenvalues for a harmonic oscillator, which is what we've got here, is if you have underdamped, an underdamped situation, which is what you'd expect in the case of a spring that, or a harmonic oscillator that just doesn't have a whole lot of drag. It doesn't have a whole lot of damping. And so it's kind of, when it moves back and forth, it's slowing down, but it's moving back and forth. And so you're getting that oscillation back and forth as it's slowing down. And so just based on the eigenvalue, you can look at it and go, I know what this thing is, how this thing is going to behave. And so continue from there. Go ahead.
So then, so we got our y of t right there, and then we broke it up, and so then we pulled the e to the negative 2t out of it, and then we were left with, k1 e 4i t. Yep. And then we did, well, obviously you can see, you go through it all, just algebra, not algebra, but yeah. And then we got down to y of t equals constant 1 e to the negative 2t times cosine 4t plus constant 2 e to the negative 2t sine 4t, with our y prime t being negative 2 constant 1 e to the negative 2t cosine t minus 4 constant 1. Okay, well, that's there okay. It is.
Yeah, you don't have to read it. I'm more interested in, it looks like you're mixing and matching methods. So at the beginning of this problem, you started by turning it into a system of first order equations, which would lead me to believe you're going to go the eigenvalue eigenvector route.
Yeah.
Right? So you found the eigenvalue, and then you switched methods on me into the, I actually found the S value method, right? And so which is it turns out okay, because in the end it gets you to the same place. But recognize you didn't have to go through all of that process all that. If you can scroll up, Quentin, you didn't have to go through all that process at the top with the turning it into a system of first order equations. You could have just jumped right to the turn the equation into a what's what I'm looking for, characteristic polynomial, right?
Okay.
And so scroll up a little bit more. Is there more information at the top there? Yeah, okay. So your original equation is y double prime plus 4y prime plus 20y equals 0. You could instantly turn that into s squared plus 4s plus 20 equals 0, which is the characteristic polynomial, right?
Okay.
So all of the rigmarole with turning it into a first order system, it's totally valid. You can totally do that. But if you're going to go that route, then you're going to find lambda, and you should then proceed to find the eigenvalue, or excuse me, the eigenvector for that.
Okay.
And then use that method. That method for this problem would have been like a 3.4 problem. Totally fine if you want to do that way. But if you're going to do it like a 3.6 problem, because it's a harmonic oscillator, you can just jump right to that characteristic polynomial and proceed. So everything that you got on there makes sense. And that's why when you get to the y of t equation, with this method, you have to then take its derivative. You actually have to do some calculus right there, exactly. You have to do the calculus to take its derivative, which is a little bit of, product rule derivatives. It's not that hard, but you have to take the derivative at that point in order to find solve the initial value problem, because you have to have both y of t and v of t. Does that make sense?
Yeah.
Okay. So you went from there, just track us through broad strokes here. Was the next thing that you did?
And then I took it, plugged in 0 for t, and then if you go down, the y 0 equals t1, which equals 2, and then y prime 0, there's all the math, which ends up equal c2 equals -1, and then I just put them in there.
Lovely. So again, we get down to the end of this, and again, that wouldn't be capital Y matrix solution Y.
No,
That would
yeah.
that'd be
Just y,
lowercase.
yep.
Yeah, just plain old lowercase y. This is a position equation, right?
Yeah.
So that's good for making predictions. Like immediately throw in a time value, it'll tell you what the position of your harmonic oscillator is. If you want to know about the phase plane, then better to have the matrix version of the solution.
Okay.
Cool. So the only other thing that I would suggest there is make sure that you are asking Maple to find the solution to verify. Right?
Yeah.
So at the very end, I don't know if you did. If you scroll down, it doesn't look like it. But
No.
if you scroll down, the very last thing that I would expect if I were doing the problem was, okay, let me check and make sure I got this solution. So desolve with my two initial conditions. You could even desolve your second order differential equation, comma, initial conditions. All nice, neat, and tidy. So any questions on that one, anybody? How about number 4? We'll try to make it rapido, because I have like less than 10 minutes.
That's me. Hold on, let's see.
Okay, so for 4, it was just solving the initial value problem. So we have our matrix, and we get the, well, we kind of, for Austin's, he started out with writing the matrix, but then we just kind of switched, just like they did, to the S thing.
Yeah, they're truly they're different methods. They're interchangeable in the sense that they both lead to the same place. One of them takes you there through matrices, so it automatically gives you the y of t and the v of t solution at the end. You don't have to do any calculus. This method, you have to do a little bit of calculus. But go ahead, sorry.
So we got -5 and 1. So our y of t was just k1 e to the -5t plus k2 e to the t. Took the derivative of that so that we could have a system to plug into, and we just plugged in the initial conditions. The e's go away because t is 0, and we got k1 is equal to 8 and k2 is equal to 3, and we just substituted that in to our k1 and k2.
Again, I assume that you checked it with Maple. You did desolve for the system or for the initial value problem.
Totally.
Totally. Okay. I'll take your word for it. The one thing I will say, I'm going to ask you the same question. Looking at lambda, you've got lambda equals -5 and lambda equals 1. At that point right there, knowing what your eigenvalues are, what kind of damping does your harmonic oscillator have? What kind of case are we? Are we underdamped, overdamped, critically damped, or undamped? Those are the 4 possibilities.
Would it be overdamped?
Yeah. How can you tell? Looking at your solution, how can you tell that it's overdamped? What's missing from that y of t equation?
Is it the sines and cosines?
There's no oscillation. This is not at all oscillating. There's no periodic nature to this solution, right? It's basically wherever you start, it's going to decay over time and head towards the equilibrium. It doesn't go, right? It just heads basically straight towards 0. Snooze. But that's handy to know. You can look at it and say 2 real eigenvalues. It's definitely 2 real different eigenvalues. It's definitely going to be a damped situation. The one thing I'll have you kind of be careful of in this case is this strictly speaking, is this a harmonic oscillator equation? You don't have the initial equation written on there, but take a look at the original problem. How can I tell this couldn't possibly be a harmonic oscillator the way we've set them up? Anybody can pipe in on this one. It's kind of one of those interesting little tidbits. Look carefully at the coefficients of your second order differential equation. It's not on the screen that you're sharing right now, but
is it the negative on the line?
You see it? It's basically implying that your spring constant is negative, which means instead of restoring your harmonic oscillator, it's pushing it away. In other words, this is not a harmonic oscillator the way we have made sense of them. So to look at this system, you can solve it using the matrix solution method. You can solve it using find the S values and plug them in like that. That's fine, but take a look. Your particular solution has an exponential decay part, but the other part is not exponential decay. It's exponential growth. It's 3e to the t, positive t, not negative. So you're okay if you look at it and go, I'm going to use the same method to solve this. It works, but you can't interpret it the same way. You can't talk about this as being, oh, clearly this is an underdamped, or excuse me, this is an overdamped harmonic oscillator. No, because if it's overdamped, that means it would head back to the origin, to equilibrium over time. And this one will not. This one blows up over time. Does that make sense? Emma, do you got a question?
Yeah, I just have a quick question.
Sure.
Is K1 and K2, are they kind of arbitrary? Because I have my 3 hooked to the E -5t and my 8 hooked to the E to the t.
They are not arbitrary.
Okay, so they should be specific.
Yeah. So
Okay.
it's either right the way it is or it's wrong.
Okay.
For those initial conditions. And of course, we only have their work to go on.
Right.
So
okay, I just wanted to make sure that it should be one way or the other, not just like willy-nilly, I guess you could say.
It is not willy-nilly because
Okay.
the eigenvalues are different, right?
Okay.
And so the exponential equations or the exponential functions are different, which means that those constants are unique to their particular location.
That's what I thought, but I just wanted to make sure.
Yep.
Thanks.
Yeah. So for this one, because we don't have anything to check it against, I'm going to leave it out there as maybe it's right. We don't know. How about number 5? No, but nobody had number 5. How about number 6?
I'll be talking. Steven will be sharing screen.
Yay.
All right, so for number 6, it is for a damped equation. we were given our the mass of 2 kilograms, the spring constant of 3 Newton meters, and the damping coefficient of 1/2 newtons per second meters. We plugged that into the equation that into the second order derivative equation that we got on page 63.
Mm-hmm.
And we did, we found general solution just by doing a simple, what is it, D solve. And that's what we got for A. For B, we, classified it as an overdamped because, underdamped case because B squared is less than 4 times the constant times M, which is the mass.
Yep.
All right. We said, okay, so that's where we started having a little bit of confusion and stuff on page 66 of the notes. Is kind of where we looked for part C. It says, if possible, state the natural period of the harmonic oscillator. And in that part, it mentioned that this motion is not actually periodic. However, we did, just based on the the notes from page, where is it?
66.
Page, there was a different one I was looking at. Oh, yeah, from page 62, where it talked about the period of a harmonic motion being t equals 2 pi over a Greek w. And then we solved for that, and that gave us a period of, what was it? 2 pi over the square root of 3 over 2. So we're still a little unsure on that. And then D, we did the D plot and stuff to show solution curves and stuff. What is it? And then we added the initial conditions as well for it. For E, find the equation of a particular solution and give us initial conditions. So the initial conditions would be based upon suppose the mass is set at initial position 3 meters to the left. So that would be, so when t equals 0, one part of it would be 3, and then the other part would be it would also be 0, so because it's -3. And then finally for G, it says using our sketch from part F, estimate the amount of time it takes for the mass to return to equilibrium for the 4th time, and we got approximately 10.3 seconds.
Okay, so can you just go back up? You did the zoom in on the graph, but on the, on the position graph before this, the one where we can see the oscillation, can you show me how you figured returning to equilibrium position for the 4th time? So where was the 4th? No, not, I don't want to see the zoomed in part. I want to see, how do you justify where you're zoomed in? So scroll up. There, on that graph right there. So show me where the 4th time is.
So I did the zooming actually. Well, I didn't really have anything to do with this.
Oh, that's fine. No, that's a good way to do it.
I just looked at the 10 and I said 10 and a bit. And so I just came down here and I kept adjusting my window until I said, that looks good enough to me.
That's perfect. What I'm asking is, how did you know to look at 10 and a bit? How did you justify that?
Because you said return.
Yep. So show me on the graph how you figured it.
So I said the equilibrium does not count, which means just 1, 2, 3, 4.
Yep. That's what I was looking for.
Okay.
Perfect. And so notice, this should look familiar if you remember the first Maple assignment that I had you guys do, where you were doing some estimating using a graph where you had to kind of zoom in, figure out how to zoom in. This is why. So you're able to make that prediction based purely on a graph, purely on that graph in particular. So any questions on that?
I had different initial conditions for part E right there.
Okay.
So
yeah, I was about to put that.
Oh, okay.
Was it -3 and 0?
Yeah.
Okay, yeah.
Okay.
Yay. Now, of course, we could, if we wanted to, tell Maple to calculate or to estimate the t value when y of t equals 0. But do you see the problem with that? You'd have to tell Maple which time when y of t equals 0, because it equals 0 periodically. And that's kind of tricky to do in Maple, like analytically in Maple. It's just easier to do a graphical solution and get a couple of decimal places and approximate it that way. Estimate it via the graph. So how are we feeling about that? If you got this one, number 5 is no trouble, right? Because number 5 is easier because it's a no damping oscillator. So that one shouldn't be any trouble for you. So here's what I'm going to do because we're running low on time. I am going to stop recording, but a couple of reminders before